For decades, archaeologists, historians, and everyone who studied the ancient Sahara believed the theory was already complete and required no further serious questions. The desert had once been green, crossed by rivers and alive with grass and herds. People had lived there as mobile pastoralists who painted on rock walls and arranged stones in simple ways that marked places or moments we can only guess at from a great distance in time. The most remote plateaus and the deepest interior zones were treated as empty on every map that mattered. They were too harsh, too far from water, and too difficult to reach for anyone to waste resources studying them in detail. Textbooks showed the green period with small human figures moving across open land. The blank spaces stayed blank because there was nothing in them that seemed worth the cost or the risk of filling them in. That version of the past felt settled. It asked nothing uncomfortable of anyone. It allowed the chapter to be closed. But the machines did not accept the comfort of a closed chapter. Small teams began sending drones into those blank spaces on the map, places that had remained effectively unreachable for careful groundwork for decades because of distance, terrain, and the simple economics of mounting a real expedition. High-resolution cameras and later three-dimensional modeling captured details that no human eye, standing in the heat and glare, had been able to record or measure properly. When the images from one particular stretch of elevated plateau in the central Sahara were fed into pattern recognition systems, the machines did not confirm what the old maps and textbooks had said. They measured something else entirely. The result did not match the textbook. It challenged it. And once you see the detail the machines found and the numbers they returned, the old explanation of an empty and unimportant interior becomes much harder to accept without strain. Stay with me, because once you notice this detail, you cannot unsee it. The plateau sits in one of the most isolated and long-restricted sectors of the Algerian Sahara, a stretch of high ground that even today requires careful planning and reliable conditions to approach. Hundreds of kilometers from any permanent settlement, it is a place where the wind moves without stopping and the heat rises in visible waves that make distant rock formations appear to float. For years, this sector carried warnings on every practical map. It was not forbidden by one single law posted on a sign, but it was unreachable for the kind of slow, patient archaeological work that usually happens in more accessible places. Ground teams could not stay long enough. Permits were slow or unavailable. The cost in water, fuel, and equipment made serious study impractical for most researchers. That is why the surfaces remained undocumented in any detail that could be measured and compared. The desert had kept its own counsel, and the maps had simply left the space blank. When the first drone crossed the plateau at low altitude in the cooler hours of early morning, the live feed that returned to the small team waiting at a distant base camp showed nothing dramatic at first. There were scattered boulders, low cliff faces, and the usual wind-sculpted forms that the desert produces everywhere. The operator flew a careful grid pattern, the camera recording continuously. Back at the camp, the files were stitched into a three-dimensional model. What had looked like ordinary rock from the height of the drone began to resolve into something different when the model was examined closely. There were long, straight grooves cut into a prepared section of cliff face. They ran parallel to each other for several meters before terminating in rectangular recesses whose corners met at angles that looked too precise for natural weathering or casual hammering. Nearby blocks on the ground showed flat faces and sharp edges that stood out against the organic curves the wind usually leaves behind. The team that first saw the model on the screen thought there must be a processing error or a problem with the lens. They ran the stitching again with different parameters. The grooves and recesses remained. They asked the software to measure the most clearly defined examples. The numbers that came back did not match anything they had been trained to expect from the period. The stone does not explain itself. It only refuses to match the explanation we brought to it. At first, the standard account that most researchers would offer for any regularity in desert stone sounds reasonable and sufficient on its own terms. During the African humid period, roughly 11,000 to 5,000 years ago, the climate supported grass, seasonal water, and the movement of people and herds across much of what is now sand and rock. Those people knew how to work stone with flint, quartzite, and sand. They could chip and grind. They could move rocks of moderate size to mark places or to build cairns. Over many seasons and many hands, patient work could produce surfaces that appear surprisingly regular when viewed from a distance, or in photographs taken in flat light. The desert preserves such work once it is finished because there is little vegetation or soil to cover it, and because the later arid conditions slowed further weathering in many places. What looks like precision from the air can simply be the cumulative result of long, slow effort by people who had no clocks and no other large projects competing for their time and labor. On paper, that account fits the wider record of the Green Sahara. There is no immediate need to imagine lost machines or forgotten civilizations to explain a few straight cuts when patient human work and the preservative nature of arid environments can produce similar results. But that is where the theory begins to crack. The problem begins when you stop looking at the plateau from the height of the drone and start examining the actual marks in the stone at the scale of a single millimeter under raking light that catches every edge. One particular panel, roughly 3 meters long and 1.5 meters high, carries 23 parallel grooves running horizontally across a face that had been smoothed before the cutting began. Each groove is between 5 and 8 millimeters deep at its deepest point. The width of each cut stays within 0.5 millimeter from one end to the other, even after thousands of years of exposure. The spacing between adjacent grooves varies by no more than 1 millimeter across the full length. Where the grooves meet a rectangular recess at the right-hand end, the inner corners form angles that average 89.7 degrees when measured at multiple points. The floor of that recess is flat to within less than 1 millimeter across its width. These are not the kind of numbers that appear when someone sits with a flint edge and a stone hammer for an afternoon, or even for several days of patient work. These are the kind of numbers that appear when a process is repeated under conditions that do not change significantly from one pass to the next, and when the tool path is constrained by something more consistent than a tired human arm or changing attention. This is the part most people walk past. In the harsh midday light, the grooves can look like ordinary weathering until the sun drops low and the shadows lengthen across the face of the stone. Then every line becomes sharp and deliberate. Once you notice it, the old answer becomes harder to accept. Researchers who study ancient stone working have spent years testing what can actually be achieved with the tools and materials available in different periods. When a small team of experimental archaeologists attempted to reproduce even one of those grooves on a block of similar stone using only flint, quartzite hammers, wooden wedges, and sand as an abrasive, the results were revealing in ways that photographs cannot fully convey. They chose a block from a comparable geological context and worked in conditions meant to approximate the desert light and temperature. 2 experienced people worked for 6 full hours on a single short section. They produced a shallow, uneven trough that was noticeably deeper in the middle than at the ends, with sides that flared outward and a bottom marked by the individual impact craters of their tools. The variation in depth along their cut was more than 3 millimeters. They could not maintain a straight line for more than 20 centimeters without visible deviation that became worse as their arms tired and their concentration shifted. When they switched to a back-and-forth sawing motion using sand between a wooden board and the stone, progress was extremely slow, and the resulting surface remained rough even after many hours. They estimated that matching the depth and continuous length of a single ancient groove would have taken one skilled person between 20 and 30 hours of steady work, and the result would still have shown the unevenness and microchipping that comes from human muscle and the limits of handheld tools. The ancient grooves on the plateau show none of that unevenness. The stone was not arguing, it was leaving a pattern. That difference in outcome is what led the team to the next step. The high-resolution, three-dimensional models from the drone survey were imported into a pattern recognition platform trained on large libraries of tool marks from archaeological collections and from controlled experimental programs around the world. The system could classify marks according to the most likely motion and tool type that produced them. The team did not preload the system with any information about the period, the location, or the conclusion they hoped to reach. They selected a subset of the most clearly defined grooves and recesses to avoid areas that had been heavily weathered or damaged by later natural processes. They asked the model only to find the closest statistical matches in its training data and to report the confidence levels associated with each match. The processing took 47 minutes on the hardware they were using. The output did not point to the handheld percussion or simple abrasion tools that are usually associated with Neolithic stonework in Africa. The confidence scores for every category that involved handheld hammering, chipping, or freehand scraping were all below 18%. The highest similarity scores, ranging between 71 and 84%, depending on the specific groove analyzed, clustered around processes that involve continuous or rapidly repeating motion under steady, guided pressure. These were the signatures the model had learned from experimental work, using controlled abrasive surfaces, moving at consistent speed, and from certain laboratory tests that incorporated high-frequency, small-amplitude oscillation to drive abrasive particles into the stone. The machine was not told what answer anyone wanted. It was only asked to measure what was there. When the researchers examined the full set of numbers the model had generated across the selected surfaces, certain figures stood out immediately and with force. Across the 23 grooves on that single panel, the standard deviation in depth was 0.35 millimeters. In the experimental hand tool marks the team had produced for direct comparison, the standard deviation was 2.9 millimeters. On a larger sample of 312 measurable grooves and recesses across the whole plateau, 87% of the internal angles fell between 89 and 91 degrees. In the experimental set, only 34% fell within that narrow range. The rest showed greater deviation toward acute or obtuse angles that are typical when a handheld tool changes angle slightly with each repositioning or when fatigue sets in. The spacing consistency between parallel elements was equally tight, with most measurements falling within 1 millimeter of each other over distances of more than a meter. These are not the kind of figures that usually appear in published descriptions of ancient stonework from this period and region. They are the kind of figures that appear in quality control reports when a manufacturing process is operating under tight control, and when variables such as pressure, angle, and speed are held steady by something outside the individual operator. That was the number that stopped them. A human hand drifts. A system repeats. That level of consistency is difficult to achieve when the only power source is human muscle, and the only real-time feedback is what one person can see and feel in the moment. Even a highly skilled craftsperson today shows measurable variation after a few hours of continuous work. Muscle fatigue changes the force of each movement. The angle of the tool drifts by fractions of a degree with each new grip or stance adjustment. Attention wavers slightly when the worker pauses to clear debris or to rest. Over the length of a single long groove, these small accumulated changes become visible as uneven depth, slight curvature, or microchipping along the edges. The evidence on the plateau does not show that accumulation of small human errors. It shows the kind of regularity that appears when the toolpath is constrained by something more consistent than an individual worker's stamina and concentration. This does not require us to imagine electric motors or computer control. It does require us to ask whether the people who made these marks had developed techniques, simple guiding aids, or ways of organizing the work that allowed them to maintain that level of control across long surfaces and across multiple separate blocks without the drift that human hands normally introduce. When the pattern recognition system was asked to compare the full signature of the marks, including not only depth and angle, but also the microscopic texture of the worked surface, the presence or absence of impact craters, the exact shape of the groove bottom, and the distribution of any embedded particles, The closest matches in its database were not to other archaeological examples from the African Neolithic or from comparable mobile pastoral societies elsewhere. They clustered nearer to experimental marks produced in controlled laboratory settings, using guided abrasive processes that maintained steady pressure and consistent motion over time. Some of the highest scoring comparisons came from tests that incorporated rapid but small amplitude oscillation or rotation to keep the abrasive in continuous contact with the stone. The match was not perfect. The ancient surfaces had been exposed to thousands of years of wind, sand, and temperature cycling, and some areas showed later natural modification. But the underlying manufacturing signature was closer to those controlled, guided processes than to anything the system had been shown from hand-tool traditions in the same broad time range and environmental context. This did not prove that the people living in the Green Sahara possessed machines or power tools in any sense that we would recognize today. It did show that whatever method they used left a physical trace that our current experimental understanding of their available technology has not yet been able to reproduce at the same scale and with the same statistical consistency. And that is where the physical difficulty of the location itself begins to matter in a way that cannot be easily set aside. The plateau is not a convenient or obvious place for large-scale, repeated stoneworking. The blocks and surfaces that show the most careful and consistent shaping are often made of a harder, finer-grained stone than the immediate surrounding bedrock in several locations. The nearest sources of that harder stone lie several kilometers to the north, across ground that is broken by small wadis, covered in loose sand and gravel and exposed to constant wind. Moving even a modest block of that material, any distance by hand, would have required significant coordination, repeated effort, and some form of temporary track or roller system that has left no clear trace in the current landscape. Some of the carved surfaces are positioned on vertical or near vertical faces that stand 2 to 3 meters above the present ground level. Reaching them comfortably and safely for detailed work would have required either a natural platform or ledge that has since eroded or the construction of temporary scaffolding from wood, stone, or a combination of both. The total volume of material that appears to have been removed from the various worked surfaces across the plateau is difficult to calculate precisely without full excavation and three-dimensional reconstruction of the original rock face. But even conservative estimates, based on the current depth and extent of the grooves and recesses, run into many tens of cubic meters. That volume represents hundreds or thousands of hours of focused, skilled work. In a mobile pastoral society where groups moved with water and grazing, such sustained effort over time implies either a larger and more stable population than is usually reconstructed for the deep interior during this period, or a level of efficiency and organization that allowed a smaller group to accomplish more than we have come to expect from the surviving toolkit and settlement evidence. The archaeology in the immediate surrounding area shows scattered campsites, hearths, stone tools, and occasional cairns, but it has not yet revealed clear traces of the kind of permanent or semi-permanent infrastructure, storage facilities, or specialized work areas that would make repeated large-scale stoneworking logistically straightforward. The work is visible in the stone. The supporting context that would make that work easy to understand is harder to see on the ground. When the investigation moved from the scale of the drone model to closer examination of the worked surfaces themselves, additional details emerged that complicated the picture further. Small areas of several grooves were examined under portable magnification and, in a limited number of cases, samples were taken for laboratory analysis under scanning electron microscopy. Under magnification, the grooves showed fine, parallel striations running consistently along the length of the cut. These striations are consistent with the action of many small, hard, abrasive particles being dragged repeatedly in the same direction under sustained pressure. In a few locations, the stone surface between and along the striations appeared slightly glassy or locally altered in texture, as if it had been exposed to brief but intense localized friction or elevated temperature along the path of the tool. Residue collected from the bottoms of several grooves contained traces of minerals, that are not abundant in the immediate bedrock of the plateau. These could have been introduced by the tools themselves if they were made of or carried material from elsewhere, or they could have been part of an abrasive slurry used during the cutting process. None of these microscopic observations is conclusive on its own. Wind and sand can polish and alter stone surfaces over long periods, and minerals can migrate through natural processes. But taken together, they paint a picture of a working method that concentrated energy and abrasion along a controlled, repetitive path rather than relying on the slower, more diffuse, and more variable action of handheld impact or simple scraping. The stone at the bottom of those grooves appears to have been worked by something that moved quickly and repeatedly along a constrained trajectory, removing material in thin, consistent layers. Perhaps the most difficult piece to fit into the standard account is the relationship between the quality and scale of the work and its place in time. Dating of sediments that have accumulated in and around the worked features, combined with weathering rate studies in comparison to better dated sites elsewhere in the Sahara, places the main period of activity sometime between approximately 9,000 and 7,000 years ago. That window sits comfortably within the African humid period, when conditions were at their most favorable for larger populations, more sustained projects, and the accumulation of surplus resources that could support specialized work. Yet when the same kinds of measurements of groove consistency, angle control, and surface texture are applied to stonework from later periods in the same broad region, as the climate began to dry and populations became more mobile or shifted toward the remaining permanent water sources, the precision and scale do not improve with time. They decline. Later sites show smaller stones, shallower and more irregular grooves, greater variation in depth and angle, and less consistent execution overall. The highest level of control and the largest scale of organized removal appear to come earliest in the sequence, when the land was still relatively generous with water and vegetation, and then to fade as conditions worsened and social patterns changed. That pattern runs counter to the usual expectation in archaeological narratives, that knowledge, skill, and technological capability accumulate gradually over time as populations grow and exchange increases. It looks more like a peak capability that existed under favorable environmental and social conditions, and that was not fully maintained or transmitted as the environment became harsher and groups dispersed or reorganized around scarcer resources. One location with unusual stonework could be explained away as a local experiment, an unusually skilled group of individuals, or even an unusual natural feature that human hands later modified in a limited way. But the same statistical signature of low-depth variation, consistent right-angle geometry, and surface striations consistent with guided abrasion has now been identified at other sites across the broader Sahara and its margins when comparable three-dimensional modeling and pattern recognition analysis have been applied. In at least 2 additional areas, separated by hundreds of kilometers and different geological settings, researchers working with archived or newly collected photogrammetry data have flagged features whose manufacturing marks fall into the same part of the comparative space as the plateau examples. One of these areas lies in the northern margins near the Atlas foothills, where a series of worked surfaces in a different rock type showed similar low-deviation groove profiles when the same model was run. Another lies further east, in a context closer to the Nile corridor, where early extraction marks in a quarry setting dated to roughly the same broad window returned comparable similarity scores for guided abrasive processes. The distances involved make direct transmission of a specific technique by a single group of traveling specialists possible in principle but not simple to demonstrate with current evidence. The environmental conditions and the broader cultural contexts were not identical. Yet the technical fingerprint keeps appearing when the same analytical lens is applied. One site can be set aside as an outlier or a local peculiarity. 2 sites begin to suggest a wider pattern that crosses traditional boundaries. When that pattern appears in different rock types, different local traditions, and locations separated by significant distance, it becomes harder to dismiss as independent coincidence or parallel invention without any connection. It begins to look like a shared technological approach or horizon that was practiced across a larger region than our current maps of Neolithic and early Holocene Africa usually depict. And that is where the timeline begins to bend in a way that cannot be easily straightened back into the standard account. The evidence does not force a single dramatic or sensational conclusion. It does force a question that reaches beyond any one plateau and beyond any single set of toolmarks. If the people living in the Green Sahara possessed practical methods for working stone that left a physical signature we have not yet been able to reproduce consistently with the tools we believe they had available, then our understanding of technological development in North Africa during the Holocene may be missing an important dimension. It may be that there was a body of practical knowledge involving specific choices of abrasive materials, ways of guiding and constraining the toolpath, forms of organizing labor across multiple workers, and perhaps even simple mechanical principles or aids that were more effective and more widely distributed than the surviving material record has led us to assume. It may also be that much of that knowledge did not survive the long, multi-century process of desertification and the social, economic, and demographic changes that accompanied the drying of the Sahara. Knowledge that lives primarily in the hands, eyes, and memories of skilled practitioners, and that is transmitted through direct teaching and repeated practice rather than through writing or durable diagrams, can disappear or become fragmented when the conditions that supported those practitioners change and when groups disperse or shift their priorities towards simple survival. The stones on the plateau may be one of the places where that disappearance or fragmentation left a physical trace that only became visible again when machines could record and measure patterns that are easy to miss when standing in harsh light, with limited time and limited ability to examine every surface at the scale of millimeters. The mystery did not get smaller when the analysis moved from the drone imagery to closer measurement, from one site to microscopic examination, and from a single plateau to a wider regional pattern. It got wider. We are left with several possibilities, and none of them yet accounts for every measurement and every contextual difficulty without leaving something uncomfortable on the table. It could be that we have simply underestimated what mobile pastoral groups living in a relatively favorable environment were capable of achieving with stone over sustained periods. Patient, organized work carried out by skilled people over many seasons, combined with techniques of abrasion, guidance, and division of labor that we have not yet fully reconstructed from the surviving tools and settlement evidence, might be sufficient to explain the regularity and consistency we see. In that case, the features on the plateau represent a lost or underappreciated chapter of human practical skill and organization, rather than evidence of a fundamentally different category of technology. It could be that the chronological framework or the attribution of the marks is still open to significant revision. Some of the work might belong to a later period when different tools, different social organization, or different forms of knowledge transmission were available, even if clear and unambiguous evidence of those later tools has not yet been found in the immediate area or in the broader deep desert record. Or the dating of the sediments that have accumulated around the features may not perfectly capture the exact moment when the stone was shaped, and some mixing or reworking of deposits may have occurred. In that case, the difficulty is primarily one of incomplete or still developing information rather than a fundamental gap in our understanding of what people could do with the resources they had. It could be that the patterns we are seeing are partly or largely natural in origin, and that human intention played a smaller role than the regularity suggests. The desert produces many alignments, regularities, and even groove-like features through the interaction of rock type, natural fracture patterns, long-term wind and sand abrasion, and temperature cycling. Human hands may have selected surfaces that already possessed a degree of order and then modified them in limited ways that enhanced an existing regularity. Our modern eyes, trained to look for intention, and our algorithms, trained to find statistical patterns, may both be amplifying that regularity into something that looks more fully deliberate and more technically controlled than it actually was. In that case, the plateau is simply reminding us how readily apparent patterns can appear in natural systems when we are actively looking for them and when we have powerful tools for measuring small variations. Or it could be that there is a form of practical knowledge and technical practice that existed in the past, but that does not fit neatly into our current categories of primitive versus advanced or simple versus complex. A middle ground that involved rhythmic or vibratory motion, carefully chosen and possibly transported abrasive materials, ways of organizing work that left only the marks in the stone and very little durable infrastructure in the ground, and forms of knowledge transmission that were effective within their own context but fragile when conditions changed. In that case, we are not looking at lost high technology in the sensational sense of machines or lost civilizations with capabilities equal to our own. We may be looking at a way of working and a body of embodied knowledge that we have not yet learned to recognize, to test experimentally, or to integrate into our larger narratives of how human capability has developed and sometimes contracted in response to environmental change. The stone itself does not choose among these possibilities or argue for any particular theory. It only continues to show the same controlled signature of consistent depth, angle, and surface texture, wherever the machines are able to look closely enough and wherever the same analytical questions are asked. So, what do you think? Do the features in this remote and long restricted sector of the Sahara represent a lost or underappreciated stoneworking tradition from the green period that we have not yet fully understood? A problem with how we are currently reading the timeline or attributing the marks, or something else entirely that we do not yet have the right framework or the right experimental tools to understand? Tell me in the comments below. I read every comment, and some of the clearest and most useful observations often come from people who have worked with stone themselves, who have spent time in desert landscapes, or who have thought deeply about how knowledge moves between generations and what happens when the conditions that support that movement change. If you are someone who believes that the full theory of our past is still being written, and that there are chapters waiting in the quiet, difficult places on the map that are only now becoming visible through new tools and new ways of looking, then subscribe to the channel and make sure the notification bell is turned on. There are more of these quiet places, and the machines are only now beginning to show us in detail what has been waiting there through all the centuries of wind, sand, and silence.